Hello, my name is Valery Sigalov from the System Internals team at Bloomberg. Some of the main responsibilities of our team include certifying the new Linux kernels and troubleshooting the performance issues. Before we upgrade to the new Linux kernels, we run a lot of regression and conformance tests to ensure the stability of the new version. But even after all these tests, we sometimes see various application performance issues with the new Linux kernels. It's common and natural for application developers to suspect that the Linux kernel is the reason that their applications don't perform as expected. And while the Linux kernel can play a big role in the application performance, it's important to recognize that it's not the only factor. In this presentation, I will show that the Linux kernel is not always responsible for the application performance problems. We investigated multiple performance issues reported by one of the application teams. One of them was significant disk latencies on the application servers. Logs told us that it started after upgrading the servers to the new Linux version. So it must be kernel then, right? After long investigation, we discovered that the large number of C groups was driving many performance issues, including the disk latency. We reduced the number of C groups, and many performance issues, including this one, have been resolved. It was indeed a kernel issue, and we worked with vendor to merge the fixes from the upstream to the Linux kernel version that we used at that time. So we reduced the number of C groups, but one of the application benchmark tests still didn't work as expected. It still felt like a kernel. What else could it be? We profiled the benchmark test and noticed that the memcopy from glibc 228 on the new Linux kernel is taking more time compared to the memcopy from glibc 217 on the old Linux kernel. We also found that the new glibc is using different memcopy implementation internally. And this implementation didn't work well with small, less than 10 bytes buffers. So we forced the application to switch to the old memcopy implementation by using the glibc tunables, and it helped to mitigate this issue. It felt like a kernel, but it was a glibc issue that was handled in the latest glibc build. So we reduced the number of C groups and we handled the glibc issue, but the application benchmark test still didn't work well. One of our regression tests showed that the clock get time overhead increased from 17 nanoseconds on the old Linux kernel to 47 nanoseconds on the new Linux kernel. It confirmed our suspicions that it had to be a kernel. So we compared the configurations between two different kernel versions and noticed that the P-state and C-state boot parameters don't work with the new Linux kernel. We replaced the P-state and C-state boot parameters with vendor-recommended boot parameters, and it helped to reduce the clock get time overhead from 47 to 23 nanoseconds. We were sure that it was another kernel bug, but it was just an incorrect configuration of the new kernel version. So we handled all known kernel and non-kernel related issues, but the application benchmark test still showed the performance degradation. So was it really a kernel? This is a question that I will try to answer in this presentation. So let me tell you a story of this investigation. So we simplified the application benchmark test to remove dependencies from all external libraries, to exclude all memory accesses and isolate this problem from any other performance issue that we investigated during that time. So we created this very simple application that calls an empty function and adds two local variables in a very long loop. After compiling and running this application on the new Linux kernel, we saw about 30% performance degradation compared to the old Linux kernel on the similar hardware. The results of running this simple application were consistent with the performance degradation shown by the application benchmark test. So we started to think that it's not a kernel-related issue and decided to explore the other possible reasons for the performance degradation. We used the following techniques during this investigation. We profiled the additional NOP instruction in the generated code. We profiled placing the local variables into the registers. We used the Intel vTune profiler to analyze the application performance. We profiled the hot code block alignment in the instruction cache. We checked the different compilation flags to optimize the application performance, and we used the profile-guided compilation for even better optimization. Some of the techniques that we used during this investigation include disassembling the object files. But please don't feel discouraged. No prior assembly knowledge is required to listen to this presentation. We also use some fundamental concepts of CPU architecture to explain the application behavior. Let's briefly review the key CPU elements such as front-end and back-end pipelines, as well as instruction and data caches. This overview will help to understand the investigation results better. Executing an instruction involves 4 basic stages: fetch, decode, execute, and write back. The fetch stage retrieves the instruction from the main memory. The decode stage translates this instruction into hardware operation. The execute stage carries out this operation, and the write back stage writes the results back into the registers in memory. These 4 stages together constitute a CPU pipeline. And specifically, the fetch and decode stages are commonly called front-end pipeline, while execute and write-back stages make up a back-end pipeline. The main purpose of front-end pipeline is to supply the continuous stream of instructions for execution and minimize the idle time the CPU is waiting for instructions to be fetched from the main memory. And this goal can be achieved when only the small number of front-end pipeline slots remain empty throughout the application execution. This concept is called front-end pipeline utilization. When discussing the application performance, we often emphasize the importance of keeping the application code and data in the main memory. And this requirement is well justified, since accessing the main memory is much faster than accessing the disk storage. However, over time, the CPU speeds increased at much faster rate than memory speeds, and it created a bottleneck when fetching the instructions from the main memory. This phenomenon is known as memory speed gap or memory wall. To mitigate the negative impact of longer round-trip time between CPU and main memory, the modern CPUs use caches, such as instruction and data cache, to keep the local copy of frequently used instructions and data. In this presentation, I will talk only about the L1 cache. It's integrated directly into the CPU core and divided by instruction and data caches. It's very small. In the CPU that we used during this investigation, it was only 64 kilobytes, 32 kilobytes for the instruction cache and 32 kilobytes for the data cache. But the L1 cache is extremely fast. For the same CPU, it was 27 times faster than the main memory. So a lot of L1 cache misses can definitely affect the application performance. The chunk of memory handled by the CPU cache is called cache line. The typical size of cache line is 64 bytes. The CPU cannot read from any arbitrary address from the main memory. The address should be aligned to the cache line boundary. So it means if, for example, you want to access the 4 bytes integer, it requires fetching the adjacent 60 bytes of data. Please remember this very important detail when organizing the memory in the application to make it cache-friendly and improve the application performance. I will talk about writing the cache-friendly code later in this presentation. The non-uniform memory access on UMA is a design that helps to optimize the CPU access to the main memory. Under NUMA, the memory access time depends on the proximity to the CPU, and the local memory can be accessed faster than the non-local memory. But the benefits of using UMA are limited to specific workloads and not as pronounced as using the CPU cache. Understanding these basic concepts should be enough for the purpose of this presentation. Let's take a look at each technique that we used during this investigation in more detail. So we decided to disassemble the code and check the differences between the code generated by GCC 8.5 on the new Linux kernel and GCC 4.8.5 on the old Linux kernel. The first difference that we noticed was the additional NOP instruction added to the empty function call by GCC 8.5 on the new Linux kernel. The NOP instruction itself doesn't emit any microcode and shouldn't affect the performance, but it still must be fetched and decoded. As I explained earlier, the front-end pipeline is responsible for fetching and decoding the instructions. And when significant portion of front-end pipeline slots remain empty, it usually means that the code size is too large and multiple accesses to the main memory are required to fetch enough instructions to fill the cache. And the additional NOP instruction or number of additional NOP instructions can contribute to the large code size and potentially create a performance bottleneck when reading the large code block. It looked like a very good explanation for the decreased application performance. We just had to prove its accuracy. The NOP instruction cannot be removed from the application code by using the compilation options. So we decided to profile it by adding the NOP instruction to the code generated by GCC 4.8.5 on the old Linux kernel. The NOP instruction can be added to the C code using the ASM keyword, as you can see on this slide. After compiling this program with GCC 4.8.5 on the old Linux kernel and making sure that additional NOP instruction was added to the generated code, we ran the application again. And as expected, the number of fetched instructions increased, but the number of cycles and execution time remained the same. So we concluded that the additional NOP instruction cannot explain the application performance degradation, but it still should be taken into consideration when investigating performance issues in the future, especially when the low front-end pipeline utilization is reported. I will show the effect of the additional NOP instruction to the application performance later in this presentation. The next finding was rather unexpected. This program is very small and it has only 2 local variables, so we expected from the compiler to put both of these local variables into the registers, since there are enough general-purpose registers available. But to our surprise, in the generated code, we saw that both of the local variables located on stack. You can see the generated code and the main function stack with the local variables on this slide. Reading the register takes only 1 cycle, and it's 4 times faster than reading the L1 cache. So it could be one of the factors for the decreased application performance. And another problem with this code is that the add instruction that adds 2 local variables cannot work between 2 operands in the memory. So additional cycles required to run the move instruction to load the content of the first operand from the memory into the register, and then the add instruction can work between the value in the register and the value of the second operand in the memory. So it looked like we found the reason for the poor application performance, right? We decided to profile this program using the register keyword with GCC 8.5 on the new Linux kernel. The register keyword is only a suggestion to the compiler to use the registers for the local variables. The compiler cannot be forced to use the registers even if there are enough general-purpose registers available. But it worked for this small program, and as you can see on this slide, the generated code was much more optimized and used registers for both local variables. The move instruction was removed, since the add instruction can work directly between the values in the registers. The number of fetch instructions decreased, and the number of cycles and execution time was significantly improved. So we solved the problem, right? Unfortunately, it couldn't explain the performance degradation on the new Linux kernel with GCC 8.5, since the old Linux kernel with GCC 4.8.5 also used the stack for the local variables. It also couldn't be used as a solution, since it required a lot of changes in the production code, and also the placement of the local variables into the registers was not guaranteed. But you should still make developers aware of this option. Because if you look at different profiling utilities, such as SREcon24, for example, all of them are heavily optimized in the source code. It's done in an effort to mitigate the differences between the compiler versions. So we decided to run this test program with Intel vTune Profiler. It's a great performance profiling tool that gives a deep breakdown of CPU execution pipeline. It generates a lot of information that can be analyzed, and it could be very beneficial if you add it to your performance regression framework, unless you are not using it already. For this small application, the main difference in vTune performance results between the old and new Linux kernel was the poor front-end pipeline utilization on the new Linux kernel. As I said earlier, the front-end pipeline is responsible for fetching and decoding the instructions. And usually these results can be explained if the code size is too large and doesn't fit the instruction cache line. But I showed when we talked about the NOP instruction profiling that it's not the case for this small application. Another explanation is that the hot pass code block spans across two instruction cache lines. The hot pass code block for this small application is the long loop that calls an empty function and adds two local variables. On this slide you can see the loop code block generated by GCC 8.5 on the new Linux kernel and how it's mapped in memory. It's small enough to fit 64-byte instruction cache line, but it spans across two separate instruction cache lines. You can see on this slide the alignment of these two instruction cache lines in memory. As I said earlier, CPU reads 64-byte chunks of memory from the address aligned to the cache line boundary. So the initial 2 bytes of the loop code block will be fetched along with 64 bytes of data from the address aligned to the first cache line boundary. And the rest of the loop code block will be fetched along with 64 bytes of data from the address aligned to the next cache line boundary. The code block spanned across two instruction cache lines is usually the reason for the performance issues in the front-end pipeline, especially for the small loops like the one in this application. Let's take a look at the effect of the loop code block alignment on the application performance. On this slide you can see the loop code block generated by GCC 4.8.5 on the old Linux kernel and how it's mapped in memory. It's exactly the same size as the loop code block generated by GCC 8.5 on the new Linux kernel, but it fits the same instruction cache line. This loop code block is fetched along with 64 bytes of data from the address aligned to the cache line boundary and executed from the instruction cache line after initial fetch and decode cycles. It explains the significant execution time difference between the old and new Linux kernels. There is one issue with this explanation. This small application runs only one type loop. And even though the loop code block generated by GCC 8.5 on the new Linux kernel spans across two instruction cache lines, as you saw on the previous slide, it's highly likely that both of these 64-byte instruction cache lines will remain in 32 kilobyte L1 instruction cache throughout the application execution. So you might ask why the code block that fits the same instruction cache line runs faster. As I said earlier, the decoder translates the instruction into hardware microoperations. And these microoperations are cached into decoded stream buffer DSB cache. And moving the loop code block into the same instruction cache line reduces the number of DSB cache misses and improves the application performance. Please take a look at the last link on the references slide for the detailed explanation about the DSB cache. We decided to check this idea by changing the layout of the loop generated by GCC 8.5 on the new Linux kernel. We used the same technique as we applied in the NOP instruction profiling by using the ASM keyword. The NOP instruction size is 1 byte, So we had to add the two NOP instructions before the loop to align it to the beginning of the instruction cache line. It significantly improved the performance of the code block generated by GCC 8.5 on the new Linux kernel and made it even faster than the code block generated by GCC 4.8.5 on the old Linux kernel. So it looked like we found the solution, right? Unfortunately, this technique couldn't be used as a solution for the same reason as using the register keyword. It required extensive changes in the production code. And even worse, to make it work, we had to know the alignment of each loop in the generated code, to calculate the number of NOP instructions to add before the loop to align it to the beginning of the instruction cache line. It was definitely impossible to implement. So we had to find a different solution, so we started to look at the optimization options. So we checked the different optimization options that could help us to achieve the same effect as the manual changes that we made in the code. The -f-align functions was the first optimization option that we tried. So when using this optimization option, all the functions in the generated code aligned to the 16 bytes boundary. On this slide you can see the code generated by GCC 8.5 on the new Linux kernel when using -f-align functions optimization option. So the two functions in this small application aligned to the 16-byte boundary. And it also pushed the loop code block into the same instruction cache line as a side effect. Please take a look at the table on this slide. It shows the differences in vTune performance results before and after using -f-align functions optimization option. The aligned code generated by GCC 8.5 on the new Linux kernel runs faster than non-aligned code generated by GCC 4.8.5 on the old Linux kernel. And also the front-end pipeline utilization improved as well. We also suspected that the placement of the local variables into remote NUMA node can affect the application performance. As I said earlier, when using NUMA, the memory access time depends on the proximity to the CPU, and the local memory can be accessed faster than the non-local memory. But as you can see from the vTune performance report, the number of remote NUMA accesses was higher on the old Linux kernel, but it didn't affect the application execution runtime. So it wasn't the reason for the poor application performance. Another optimization option that we tried is -f-align loops. When using this option, all the loops in the generated code aligned to the beginning of the instruction cache line. This option is not as straightforward as the -f-align functions optimization option. The compiler is using the same technique as we used to align the loop to the beginning of the instruction cache line by simply adding the NOP instructions before the loop. And it can be beneficial for the longer loops, but it can have an opposite effect for the shorter loops, since the penalty of entering the short loop through the aligned code can be too high to justify this change. There is another optimization option, -f-unroll loops, that can help to mitigate the negative effect of the loop code block alignment. All the alignment options are included into -02 optimization level with many other optimization options. Using alignment options can increase the code size and potentially create a performance bottleneck in the front-end pipeline. There is another optimization level, -OS, that includes all optimization options from -02 optimization level without the alignment options. So you can use -OS with only some alignment options, like -f-align functions, for example. But usually -02 is recommended for the production code. There is even higher optimization level, -03, but it turns on the more expensive optimization options, such as inline functions, for example. When using this option, the code size can significantly increase and create a performance bottleneck in the front-end pipeline. So this option should be considered with care. There are certain drawbacks when using the higher optimization levels. First of all, it decreases the debugging visibility. It also increases the compilation time and the memory consumption during the compilation. All this should be taken into consideration as well. Another technique that we use to improve the application performance is profile-guided optimization. PGO is a method used by GCC to produce an optimal code by using the application runtime data. And because this data comes directly from the application, the compiler can make much more accurate guesses. PGO is straightforward. Collect the profile information about your program, then recompile it again by feeding the compiler with the profiling info. The compiler will use this info to generate a faster binary. The first phase is instrumented compilation. Instrumented compilation produces an executable that contains probes in each of the basic blocks of the program. Each probe counts the number of times the basic block runs and records the direction taken by the branch. The second phase is profiled execution. During the second phase, you need to run the different real-life loads to collect as much data as possible. The instrumented program generates a profiling data file that contains counts from the program execution. The information from the profiled execution is fed back to the compiler. This data is used to make much better estimate of the program's control flow. The compiler is using this information to produce an executable file, relying on this data and not on the static optimization flags. The PGO-generated binary is usually more optimized than the binary generated using -02 optimization level. The main problem when using PGO is to find enough real-life loads to cover every possible execution path and collect as much data as possible. We used Python 3.12 to check the performance improvements when using PGO. Python has a built-in PGO compilation option, Enable Optimizations. This option builds Python with PGO using the Python regression tests as real-life loads to generate profiling data. We built two versions of Python, with and without PGO, and used PyPerformance benchmark suite to compare the performance differences between two versions. The PyPerformance benchmark suite runs 83 different tests, so the results are quite comprehensive. I included only a small number of tests into the table on this slide, but you can see a very significant performance improvement when using PGO. I think you should give it a try. In this presentation, I tried to address the common misconception around blaming the Linux kernel for the poor application performance. The Linux kernel is a very complex piece of software, and sometimes it can be the reason for the application performance issues. But the main lesson that we learned during this investigation is that the holistic approach is very important when investigating any performance issue. Instead of blaming the Linux kernel, you should work together with application developers, utilize the different performance tools, and investigate the potential bottlenecks in the application code. This is the only way to effectively diagnose and to resolve any performance issue, and learn about the Linux kernel role in the application performance. I would like to finish this talk with a side note. I have talked about using the compilation options and profile-guided optimization to improve the application performance. But I also showed the importance of keeping the hot code blocks in the instruction cache to optimize execution. If you really care about the application performance, you should write the cache-friendly code. This means keeping the data in contiguous memory locations, since CPU is reading the contiguous blocks of instructions and data for performance optimizations. This also means keeping the function stack as small as possible. Using the small data structures. Using the cache-friendly data structures, such as arrays for example, and breaking the large loops into small ones. You can watch an excellent presentation, CPU Cache and Why You Care, for more details. On this slide you can find the list of all books, articles and presentations that we used during this investigation. I hope you will find this useful. Thank you.